Greetings and salutations. Today we're going to talk about how you make and use and do calculations with an inexpensive dielectric properties measuring device built on a old frequency meter. So let's take a look at what we can do here. By way of backgrounds, there are lots of different ways to measure dielectric properties. Agilent has taken the kind job of writing a whole booklet on this topic that's about 20 to 30 pages long. If you go ahead and look that up and read that, you will learn all sorts of useful bits and tidbits of information. Long story short, there's different ways to do it. People have come up with lots of different methods, fundamental methods, and they are listed here. There's coaxial probes, which work great if you're measuring liquids and semi-solids and things, but not great for some other things. Transmission line, again, works well for lossy materials, difficult to use with lower loss materials sometimes. The free space method is typically used to determine the properties of housing materials, particularly at high frequencies. We're talking 5 to 50 gigahertz, etc. The resonance cavity method is what we're going to be talking about today. It is accurate, which is a plus, and it's also very good at the lower microwave band, lower frequencies, what I'm going to call lower frequencies. I'm talking 1, 2, 3, 4 to 10 gigahertz works particularly well. If you get too high, then your cavities get tiny, although there are resonant cavities that work up to 20 to maybe 50 gigahertz, etc. We won't be talking about those. And the parallel plate method, of course, is literally a capacitor, and you're just measuring the dielectric properties of that capacitor by sticking the dielectric between the two plates. All right. So resonant cavities, again, in the lovely publication from Keysight, Agilent, HP, it shows their resonant cavity method. They essentially attach a waveguide and create a cavity, and then you measure S21 through the cavity. You put tiny coupling holes on the end to achieve the resonance within the cavity, and then you throw a little hole in the center and you put your sample down through the hole to measure how it impacts the resonance of the chamber. Beautiful method. I looked at trying to get this lovely cavity that they have there, and it's part of a special kit, and it costs more money than I make in a few days, so we're going to skip that. For a high Q system, for any high Q system, you need a good conductor. So copper waveguides or something like that. Silver is lovely and slightly better. Gold also works, though actually silver, I believe, is a better conductor. Anyway, it is difficult and inexpensive to find, difficult to find inexpensive and high quality resonance cavities. Some of these resonant cavities date back to the 1950s. The waveguides, if you use them, typically require some sort of modification. And if you're using waveguides, you're generally limited to a very specific frequency or the lowest frequency of the waveguide. So as an alternative, I decided to look into microwave frequency meters, which were made in the 1950s and 60s. They're silver coated. They have really high Q cavity resonances, and they are lovely in that respect. So at the bottom here are 3 examples of these frequency meters. The first 2, as you can see, attached to waveguides. The third one has N connectors. This is by HP, I believe. The problem with these structures is that due to their screw mechanism here, it is difficult to get a sample into the chamber without mucking up the chamber, and it's difficult if you unscrew it and remove all the housings on the outside to hold everything in place. So while not impossible, it was a pain in the neck, so I decided to look for additional frequency meters, and I came across this one. This is an FXRN410A made by a lovely machine shop in Woodside, North New York. It appears probably in the 1960s, maybe. The thing I like about this one is it has N connectors on either end, which makes it really easy to attach to your instrument. It has a horizontal construction, which makes it easy to put things in. It has resonances. The primary resonance is at 1 gigahertz, and then it has overtones, which are called harmonics in English, between at 2, 3, and 4 gigahertz. It is physically robust. It could be used to whack somebody over the head, and you would not like the results. It is silver plated on the resonance cavity, which makes it really high Q, and it has the slot on the side. Actually, it's 2 slots on either side, which allows you to insert materials to measure them. Samples can only be inserted to a depth of about 11 millimeters, and that's because there is a coax running through the center. You can see the coax here in the lower right-hand picture. This coax goes directly through the center of the cavity, and it has a nice little slot. The reason for this slot is going to come apparent in the next slide, but essentially that's what leaks the signal out of the coax into the chamber, which allows it to resonate. And that's the frequency that we can see resonating, and when we insert our material, that's the frequency that shifts due to the cavity resonance shifting due to the loading of the material. All very cool, all very straightforward. The other thing I was going to show is the picture on the right here. This is the inside of the cavity. You can see these tiny little spring fingers all over the place. So this is the original mechanism which slides back and forth to change the size of the cavity. In our embodiment, we are not going to be changing the size of the cavity. We could do that, but it just makes life more complicated and it's unnecessary for what we're doing here. So, talking a little bit about the cavity structure, the original cavity structure, you essentially have small openings or coupling mechanisms on either side, and you have a material sample through the center. You put the sample in the center, and you have your S1, S2 ports. You measure S21 or the signal through that cavity. Ours is just a little bit different. So again, we have the 2 ports at the edges of the cavity. We have the cavity. We put the sample in the center of the cavity. But we have a coupling slot, and that coupling slot allows a little bit of energy to leak out the coax and resonate in the chamber. And by looking at the signal that comes back, we can see which frequency is resonant. And that resonance changes, of course, when we add the sample to the cavity. And of course, the sample is going to absorb energy if the Q is low, and we will see that as well. In terms of modes, we have, of course, the primary mode, we have the second mode, we have the third harmonic and the fourth harmonic. These have frequencies attached to them, obviously, and it's the CCs multiplying by 2, 3, 4. These are the particular frequencies of my chamber. Your chamber, if you decide to use this method, may be a little bit different, but I've tested 2 so far, and they are quite similar, only differing in a few megahertz. So I think you'll get something pretty similar to this if you build this device. The measurement, in other words, the sample needs to be inserted at the peak E-field location, so you can see that that location is in the center for the primary mode and then moves off-center for the subsequent modes. I've marked mine here on the cavity with a number 1, 2, and 3, depending on the frequency, essentially 1 gigahertz, 2 gigahertz, 3 gigahertz, and those are the locations where you want to place the sample. In terms of the calculations, obviously it's lovely to get this data out, but if you want to do something with the data, you've got to look at the frequency shift, you've got to look at the change in Q, and you've got to look at other properties in order to get out the dielectric properties of the material. So what do we care about? Here are the 2 equations which were so kindly provided by HP Agilent. The first one is epsilon prime, the second one is epsilon double prime, and once you know epsilon double prime, you can use that along with epsilon prime to calculate the tan delta, and that is your material loss. So that's lovely. So what are we going to do here? Well, we need to know the volume of the chamber. We need to know the frequency, original frequency, and the shifted frequency. We need to know the volume of the sample contained within the chamber. And based on those, the cavity frequency and the shifted frequency with the sample inserted, we can calculate epsilon prime. Now, when we do the calculations, and I've done the calculations, I don't get the result, which is unfortunate, but again, we are looking at a cavity which is a symmetric cavity roughly, but it has the coax running through the center, not intended with the original equations, and it also has the sample which is offset on one side, so it's only loading half the chamber. It's not actually going through the full chamber. And I think because of that, it throws off the calculations a little bit. So what I've done is I've added a fudge factor of 1.7. In this case, it's empirically derived based on the dielectric properties of Teflon, pardon me. When we do that and make that one adjustment, we keep the epsilon double prime equation the same. We do have to calculate the Q values of the sample. The Q values are calculated based on the shape of the curve here. Essentially, you calculate it based on the width of the frequency, and you compare that with the Q of the unloaded chamber. So I've chosen to make a bunch of samples and measure a bunch of samples. Some of these materials are known, some of them are not known. The sample number 1 here at the bottom is Teflon. Number 4 is acrylic. Number 5 is FR4, a PCB material. Numbers 7, 8, and 9, as you can see, are samples of wood. And 10, 11, and 12, these at the top here, are all various types of foam, which are very low loss. A little information about the samples. You want to make them at least 30 millimeters long. You want to make them 3 to 8 millimeters wide. And I find that being closer to the 8 is going to give you a more robust result. If you get over 10, then you will find that you have some additional error based on your sample width, which is calculated here in this chart at the bottom. So to keep that error down to a few percent, you really don't want to go above about 10 millimeters width. And of course, this becomes more significant as you have higher frequencies, because at higher frequencies, your E-field location becomes more critical. So something to keep in mind when you're making your samples and testing your samples. All right, with all that done, we ran the calculations as shown in the previous equations, and these are the results. So the Teflon results you can essentially disregard, at least in terms of E prime, because these were used for calibration. Now note, I only used it to calibrate it at one frequency. I used the same constant for all frequencies, but again, this is empirical, so it's used to calculate. The rest of these results will give you an indication of how well the method is working. The acrylic sheet at 2.69 is actually pretty dang good. A lot of the plastics, PC, PCABS, tend to be right around 2.7 at these frequency ranges, so I'm pretty happy with that result. FR4 came in about 4.8 to 4.55, expecting a value a little bit closer to 4.0, although some FR4 materials do have a slightly higher dielectric constant than 4. So I don't believe that's too far off. The wood properties, there's nothing in the literature, and wood tends to vary based on type, density, growth rings, blah, 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 blah. So unclear whether or not these wood values are accurate or not. The losses for the wood samples are quite high, which you'll note here. And it's interesting also how the wood samples do tend to change dielectric constant over frequency. The various foam materials had dielectric constants between 1.03 and 1.07, which seems very reasonable to me. And they also had very low losses, which again seems quite reasonable to me. We had one sample of a glass-filled plastic here at the bottom, which ended up having quite a high dielectric constant and relatively moderate loss. That's what I got for you today. Thank you for your time, and feel free to leave any questions that you may have in the comments. Take care.